Hello, in this lecture we will prove Stewart's theorem in two different methods. In a nutshell, Stewart's theorem yields a relation between the lengths of the sides in the triangle to the length of its CVN. So here we have triangle ABC. The length of side AB of triangle ABC equals to 2 units, side AC of triangle ABC equals to B units, side BC of triangle ABC equals to A units in its length. In addition, we know that line segment BD equals to M units, and finally line segment DC equals to N units in its length. And the CVN in this triangle ABC is line segment AED, and line segment AED equals to the units in its length. So, I repeat again, that Stewart's theorem yields a relation between the lengths of the sides of the triangle ABC to the length of its CVN. That is to say D. The length of the CVN AD is D. And according to Stewart's theorem, B squared times M plus C squared times N equals to A, open brackets, inside the brackets we have D squared plus M times N. Okay? So, we'll prove Stewart's theorem. We'll prove that this equation is true in two different methods. So, in the first method, we'll do a construction from point A, we will draw perpendicular on BC. Okay. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC as E. And we'll define this line segment ED as X. We'll also define the length of this line segment AE is H. So here it is very easy to see from knowing that the length of this line segment EC equals to ED plus DC, that is to say EC equals to X plus N. Okay, you can write down that this line segment EC is equal to X plus N, EC equals to X plus N, and what is the length of line segment BE? For knowing it is very easy to see that BE equals to BD minus ED. BD minus ED equals to BE. I write it down. BE equals to BD minus ED. So BE equals to BD is M, so substitute BD by M. Minus ED. ED equals to X, so substitute ED by X. So in conclusion, we found out that BE equals to M minus X units in its length. So can I down here the drawing that BE, this line segment BE equals to m minus x units in its length. Okay. In the next step, we will implement the Pythagoras theorem on the right triangle, triangle AED. Repeat again, we will implement the Pythagoras theorem on the right triangle, triangle AED. In the right triangle, triangle AD, first of all, the Pythagoras theorem states that in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Again, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, the hypotenuse in this right triangle, triangle AD is AD, therefore the square of the hypotenuse is AD square, and it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to AE square plus ED square. So we actually found out that in the right triangle, triangle AD, according to the Pythagoras theorem, AD square equals to AE square plus ED square. Okay. Here by PT is a version for Pythagoras theorem. AD equals to the units in its length, therefore AD square is D square. And it is equal to AE square. AE is h, therefore A square is h square, plus ED square. ED is x, therefore ED square is x square. So, in conclusion, we found out that in the right triangle, triangle AEB, right triangle, D square equals to h square plus x square. In the next step, we will implement the Pythagoras theorem on the right triangle, triangle AEC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle AC is AC, therefore the square of the hypotenuse is AC square. And it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to AE square plus EC square. Repeat again, in the right triangle, triangle AEC, by PT is a version from Pythagoras theorem. According to the Pythagoras theorem, AC square equals to AE square plus EC square. This is equation number 1. AC equals to B units in its length, therefore AC square is B square. And it is equal to AE square. AE equals to H units in its length, therefore AE square is H square plus EC square. We already found out that EC equals to x plus n, therefore we substitute EC by x plus n. So if EC equals to x plus n, it means that EC squared equals to x plus n squared. In conclusion, found out that in the right triangle EC, b squared equals to h squared plus x plus n squared. Here we'll open the brackets on this side of equation, number 1, and we get that according to equation number 1, b squared equals to h squared plus x plus n squared. X plus n squared equals to x squared plus n squared plus 2 times x times n. In this equation number 1, we have h squared plus x squared, and we have already found out that h squared plus x squared equals to d squared. So we substitute h squared plus x squared by d squared in this equation number 1, and we get that according to equation number 1, b squared equals to h squared plus x squared is d squared plus n squared plus 2 times xn. This is equation number 1. B squared equals to d squared plus n squared plus 2 times xn. In the next step, we'll implement the Pythagoras theorem on the triangle ABE. Repeat again, we'll implement the Pythagoras theorem on the right pink triangle AB. Repeat again by PT is a version for Pythagoras theorem. So on the right pink triangle AB, according to the Pythagoras theorem, AB squared equals to AE squared plus BE squared. Repeat again, in the right pink triangle AB, according to the Pythagoras theorem, AB squared equals to AE squared plus AB squared. Okay. AB equals to C units in its length, therefore AB squared equals to C squared, and it is equal to AE squared. A equals to H, therefore E squared is H squared, plus BE squared. We have already found out that BE equals to M minus X, so we substitute BE by M minus X. So if BE equals to M minus X, it means that BE squared equals to M minus X squared. So in conclusion, we found out that in the right pink triangle AEB, this is equation number 2, that C squared equals to S squared plus M minus X squared. Here we'll open the brackets on this side of equation number 2, and we get that according to this equation number 2, C squared equals to H squared plus M minus X squared. M minus X squared, according to the algebraic identity that A minus B squared equals to A squared plus B squared minus 2 times AB, will be equal to M squared plus X squared minus 2 times MX. Here, in this equation number 2, we have H squared plus X squared. We have already found out that H squared plus X squared equals to this squared, so we substitute x squared plus x squared by d squared in this equation number 2, and we'll get that c squared equals to h squared plus x squared, that is d squared, plus m squared minus 2 times mx. This is equation number 2, and we already found out that according to equation number 1, b squared equals to d squared plus n squared plus 2 times xn. Okay. In the next step, we'll create equation number 3 in the following way. We'll multiply equation number 1 by n. Then we will multiply equation number 2 by n, and then we will add the two equations together. This will give us equation number 3. Okay. Repeat again the multiplication of equation number 1 by n plus the multiplication of equation number 2 by n, and then the addition of two equations together yields equation number 3. So we do it in 2 steps. In the first step, we will multiply the right side of equation number 1 by m. This is the right side of equation number 1. We will multiply it by m, and it will be m. Inside the brackets we have d squared plus n squared plus 2 times xn multiplied by m. And we will also multiply the right side of equation number 2 by n. This is the right side of equation number 2, and we will multiply it by n. So n, inside the brackets we have d squared plus m squared minus 2 times mx. And it must be equal to the multiplication of the left side of equation number 1 by m. In the left side of equation number 1 we have b squared, so it is mb squared, plus the multiplication of the left side of equation number 2 by n, so it is n. In the left side of equation number 2 we have c squared, so it is nc squared. Okay. So this is equation number 3. We'll open the brackets on this side of equation number 3, and we'll get that according to this equation number 3, we have here m times d squared is md squared, plus m times n squared is mn squared, plus m times 2xn is 2xmn, plus, we'll open the brackets here, n times d squared is nd squared, plus n times m squared is nm squared, plus n times minus 2mx is minus 2mxn, or 2xmn. And it is equal to mb squared plus nc squared. So in this equation, in this side of equation number 3, we have plus 2xmn minus 2xmn is 0. So those two expressions will get cancelled. What is left from equation number 3 after we cancel the two expressions? In this side of equation number 3, we have actually md squared plus mn squared plus nd squared plus nm squared equals to mb squared plus nc squared. So actually, this is equation number 3 after we cancel the two expressions. In the next step, we take out d square as a common factor from this expression md square, and from this expression md square. So what is left from md square after we took from it d square as a common factor? What is left actually m. What is left from nd square after we took from it d square as a common factor? What is left is actually n. Then we took mn as a common factor from mn square, and also as a common factor from nm square. So what is left from nm square after we took from it nm as a common factor? What is left is actually m, plus what is left from n square after we took from it mn as a common factor? What is left is actually n. And it is equal to mb square plus nc square. In the next step, we took m plus n out as a common factor from those two expressions. Okay, so m plus n is taken out as a common factor. What is left from this square times m plus n after we took from it m plus n as a common factor? What is left is actually d square. What is left from mn times m plus n after we took from it m plus n as a common factor? What is left is actually mn. And it is equals to b square m plus c square n. Here m plus n equals to a. It is very easy to see it in the drawing. According to our definition, BC equals to A from one side, but from the other side, it is very easy to say that BC equals to BD plus DC. That is to say, BC equals to m plus n from one side, but from the other side, BC equals to A, therefore A equals to m plus n. Very simple. So we substitute m plus n in this equation number 3 by A, and we'll get that here m plus n is A, and inside the brackets we have d square plus m plus n, that is equal to b square m plus c square n. And this is exactly the equation of Stewart's theorem. So we succeeded to prove Stewart's theorem according to the first method. In the next step, we'll prove that Stewart's theorem is true according to a different method, according to a second method. In the second method, we will define this angle ADB as theta. Therefore, the adjacent angle ADC must be equal to 180 degrees minus theta, according to rule number 1, that the sum of the angles on one side of a straight line is equal to 180 degrees. BC is a straight line. If we focus on the upper side of the straight line, BC at point D, here the sum of the angles must be equal to 180 degrees according to rule number 1. So which angles we have at the upper side of BC at point D? We have this angle, this theta, plus the missing angle ADC must be equal in total to 180 degrees. Therefore, the missing angle must be equal to 180 degrees minus theta. Why? Because 180 degrees minus theta plus theta is 180 degrees, exactly according to rule number 1. Okay? In the next step, we'll implement the law of cosines in the green triangle ABC. And then we implement the same law, the law of cosines, in the pink triangle ADC. I will remind to you what is the law of cosines. Actually, the law of cosines is true in any triangle. So this triangle ABC could be any triangle. The length of side AB is A units, the length of side AC of triangle ABC is B units, and side BC equals to C units in itself, and also we know that the angle BAC, this angle equals to theta. Then according to the law of cosines, C square equals to A square plus B square minus 2 times A times B times cosine theta. From this equation, it is very easy to arrive to this equation. By adding to this equation 2 times AB cosine theta, then we'll subtract from this equation C square, and then we'll divide it by 2 times AB, and we'll arrive to this equation that cosine theta equals to A square plus B square minus C square over 2 times A times B. So we'll implement the law of cosines in the green triangle ADB. According to the law of cosines in the green triangle ADB, cosine theta equals to d square plus m square minus c square over 2 times d times m. So actually, this equation number 1, is the implementation of the law of cosines in the green triangle ABD. Okay, cosine theta equals to d square plus m square minus c square over 2 times dm. Okay. In the next step, we will, so this is triangle ABD, the green triangle. In the next step, we'll implement the law of cosines in the pink triangle ADC. So, according to the law of cosines in the pink triangle ADC, we'll get that cosine 180 degrees minus theta equals to d square plus n square minus b square over 2 times d times n. Here, equation number 2 is the implementation of the law of cosines in the pink triangle ADC. We have the algebraic, the trigonometric identity that states that cosine 180 degrees minus theta equals to minus cosine theta. So according to this trigonometric identity, we'll get that in the question number 2, cosine 180 degrees minus theta equals to minus cosine theta, and it is equals to d square plus n square minus b square over 2 times d times n. In the next step, we'll multiply this equation number 1 by minus 1, and we'll get cosine theta times minus 1 is minus cosine theta, and it is equal, we'll multiply the other side of course by minus 1 also, so it is minus, and inside the brackets we'll have d square plus m square minus c square over 2 times d times m. So actually we have two different expressions for minus cosine theta, so we'll create equation number 3 that states that minus cosine theta according to equation number 1 must be equal to minus cosine theta according to equation number 2. Okay, so minus cosine theta according to equation number 1 equals to minus d square plus m square minus c square over 2 times d times m, and it must be equal to minus cosine theta according to equation number 2. Minus cosine theta according to equation number 2 equals to d square plus n square minus b square over 2 times d times n. Okay. Here we will multiply this equation number 3 by 2d, and we'll get in this side of equation number 3 we have 2d over 2d is 1, so 2d will get cancelled, so in the denominator of this side of equation number 3 we left only with m. The numerator didn't change. In the numerator we have the same expression, that is minus, inside the brackets we have d square plus m square minus c square equals to, multiply also this side of equation number 3 by 2d. 2d over 2d is 1, so 2d will get cancelled, and the denominator we left only with n. The numerator didn't change. In the numerator we have the same expression, that is to say d square plus n square minus b square. In the next step we will cross multiply this equation number 3, and we'll get that according to equation number 3 minus n, inside the brackets we have d square plus m square minus c square equals to m, inside the brackets we have d square plus n square minus b square. Actually, this is equation number 3 after we cross multiply it. In the next step we will open the brackets on both sides of this equation number 3. And we'll get that according to this equation number 3, minus n times d square is minus n d square. Minus n times m square is minus nm square. And finally, minus n times minus c square is plus nc square. Why? Because minus times minus is plus. And it is equal to m times d square is md square plus m times n square is mn square plus m times minus b square is minus mb square. In the next step, we will add to this equation nd square. So if you focus on this side of equation number 3, nd square minus nd square is 0. We'll add also to this equation number 3, nm square. So in this side of equation number 3, we will have nm square minus nm square is 0. And finally, we subtract from this equation number 3, nc squared. So in this side of equation number 3, we'll have nc squared minus nc squared, that is 0. So in total, in this side of equation number 3, we'll have 0, if nothing. In the other side of equation number 3, we've already had the expression md squared plus mn squared minus mb squared. And we have to add to this side of equation number 3 nd squared. We have to add to it also nm squared. And also we have to subtract from this side of equation number 3 nc squared. Okay. And okay, in the next step, we will take out this square as a common factor from nd square and also from md square. So what is left from md square after we took from it this square as a common factor? What is left is m. What is left from nd square after we took from it this square as a common factor? What is left is actually n plus, we will take mn out as a common factor from mn square and also from nm square. What is left from nm square after we took from it mn as a common factor? What is left actually m. What is left from mn square after we took from it mn as a common factor? What is left actually n. We have also here minus mb square minus nc square, and is equal to 0. In the next step, we will add mb square and also nc square to this equation number 3, and we will get that d square m plus n plus mn m plus n mb square minus mb square is 0, and nc square minus nc square is 0. On the other side of the equation, we will have mb square plus nc square. In the next step, we will take out m plus n as a common factor from this expression and also from this expression. So what is left from this square m plus n after we took from it m plus n as a common factor? What is left actually this square? What is left from mn times m plus n after we took from it m plus n as a common factor? What is left actually mn? And it is equal to b square m plus c square n. We have already found out in the first method, it is very easy to see it from the drawing also, that m plus n equals to a. So we'll substitute m plus n by a in this equation number 3. And we will get that according to equation number 3, here we have m plus n, that is a. And inside the brackets we have d square plus m times n, that is equal to b square m plus c square n. And this is exactly the equation of Stewart's theorem. So we succeeded to prove Stewart's theorem in 2 different methods. In the next step, I will summarize the lecture. We'll start with the first method, of course. In this lecture, we proved Stewart's theorem in two different methods. In a nutshell, Stewart's theorem yields a relation between the lengths of the sides in the triangle to the length of its civilian. And according to Stewart's theorem, the following equation is true, that b squared times here, I will repeat that side AB in triangle ABC is equal to C units in its length, side AC equals to B units in its length, side BC equals to A units in its length, side line segment BD equals to M units in its length, and finally line segment DC equals to N units in its length. And the civilian in this triangle ABC is AD, that is equal to D units in its length. So we have in Stewart's theorem the relation between the lengths of the sides in the triangle to the length of its civilian AD. The civilian AD equals to D units in its length. And according to Stewart's theorem, the following equation is true, that b squared times m plus c squared times n equals to a, we'll open the brackets, inside the brackets we'll have d squared plus m times n. Repeat again, b squared m plus c squared n equals to a, inside the brackets we have d squared plus m times n. We proved this equation in two different methods. In the first method, we did a construction that is to say, from point A we draw perpendicular on BC. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC as E. Then we define side ED as X. We define line segment ED as X. We define line segment AE as H. Here EC equals to x plus n, it is very easy to see from the domain, and line segment BE equals to m minus x, right? Because it is BD minus ED. BD is m, ED is x, so in total BE equals to m minus x. Then we implemented the law of cosines in this great triangle AED. The law of cosines implemented the Pythagoras theorem in this triangle AD. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the source of the perpendiculars. So in this right triangle AD, the hypotenuse is AD, therefore the square of the hypotenuse is AD square, and it must be equal to AE square plus ED square. Repeat again. In the right triangle AED, this is triangle AED actually, the triangle AED, the right triangle is triangle AED, as you can see in the drawing. In this triangle AED, AD square equals to AE square plus ED square, according to the Pythagoras theorem. AD equals to D, therefore AD square is D square. Here AD square is D square. AE equals to H, therefore AE square is H square. AE square is H square, and finally ED equals to X, therefore ED square is X square. So in conclusion, found out that in the right triangle AD, D square equals to H square plus X square. Then implemented the Pythagoras theorem in the right triangle that is partially green, AEC. Okay, in this right triangle AEC, according to the Pythagoras theorem, AC square equals to AE square plus EC square. Again, AC square equals to AE square plus EC square. Repeat again, in the right triangle AC, according to the Pythagoras theorem, AC squared equals to AE squared plus AC squared. AC equals to B, therefore AC squared is B squared. Here AC squared is B squared. AE equals to H, therefore A squared is H squared. AE squared is H squared. And finally, EC equals to X plus N, therefore EC squared is X plus N squared. EC squared is X plus N squared. Then we open the brackets of this side of equation number 1 and found out that according to equation number 1, B squared equals to H squared plus X plus N squared equals to X squared plus N squared plus 2 times Xn. Here in the equation number 1 we have X squared plus X squared, and we already found out that H squared plus X squared equals to this square. So we substitute X squared plus X squared in this equation number 1 by this square. And we got that B squared equals to H squared plus X squared is this square plus N squared plus 2 times Xn. This is equation number 1. And then we created equation number 2 by implementing the Pythagoras theorem on the pink right triangle, triangle AB. In the pink right triangle, triangle AB, according to the Pythagoras theorem, AB squared equals to AE squared plus EB squared. Repeat again, AB squared equals to AE squared plus EB squared. Here, AB squared equals to AE squared plus EB squared. So here AB is C, therefore B squared is C squared. So you can see here AB squared is C squared. AE is H, therefore A squared is H squared plus BE squared. BE equals to M minus X, therefore BE squared is M minus X squared. So in conclusion, found out that according to equation number 2, C squared equals to H squared plus M minus X squared. Here we open the brackets of this side of equation number 2 and found out that according to equation number 2, C squared equals to H squared and A minus X squared according to the algebraic identity that A minus B squared equals to A squared plus B squared minus 2 times AB, we get that A minus X squared equals to M squared plus X squared minus 2 times MX. Here again we have H squared plus X squared, and we already found out that H squared plus X squared equals to D squared. So we substitute H squared plus X squared by D squared in this equation number 2, and we found out that C squared equals to H squared plus X squared is D squared plus M squared minus 2 times MX. Okay, so this is equation number 2, and according to equation number 1, we have already found out that B squared equals to D squared plus N squared plus 2xn. Then we created equation number 3 in the following way. We multiplied the equation number 1 by n. Then we multiplied the equation number 2 by n, and then we added the two equations of each other. This is equation number 3. Okay, we did it in 2 steps. First of all, we multiplied equation number 1, the right side of equation number 1. This is the right side of equation number 1 by m. So it is m times d squared plus n squared plus 2 times xn. Then we multiplied the right side of equation number 2 by n. This is the right side of equation number 2. And we multiplied by n. So it is n. Inside the brackets we have d squared plus m squared minus 2 times mx. And it must be equal to the multiplication of the left side of equation number 1 by m. On the left side of equation number 1 we have b squared, so it is mb squared plus the multiplication of the left side of equation number 2 by n. On the left side of equation number 2 we have c squared, so it is nc squared. Okay. In the next step we open the brackets on this side of equation number 3, and we got that m times d squared is md squared plus m times n squared is mn squared plus m times 2xn is 2xmn. Then we open also the brackets here of this expression. N times d squared is nd squared plus n times m squared is nm squared plus n times 2mx is minus 2mx, 2xmn. And it must be equal to mb squared plus nc squared. So in this side of question number 3 we have 2xmn minus 2xmn is 0, so those two expressions will get cancelled. And this is equation number 3 after we cancel the two expressions. mb squared plus nm squared plus nd squared plus nm squared equals to mb squared plus nc squared. In the next step we took this square as a common factor from nd square also, and also from nd square, and also from nd square. So inside the brackets we have left only m plus n, and then we took a common factor of m times n from mn square and also from nn square. So inside the brackets we left only with m plus n, and it is equal to mb square plus nc square. Then we took m plus n out as a common factor from those two expressions. So inside the brackets we left with d square plus nm, that is equals to b square m plus c square n. Then m plus n equals to a. It is very easy to see in the drawing here that m plus n equals to a. Why? Because side BC from one side equals to m plus n. From the other side, side BC equals to a, therefore m plus n equals to a. Very simple. So therefore we substitute m plus n in this equation number 1 by a, and we got that here m plus n is a, so inside the brackets we have d squared plus m times n, and it is equal to b squared m plus c squared n, and this is exactly Stewart's theorem. So we proved Stewart's theorem according to the first method. Then we proved Stewart's theorem according to the second method. In the second method, we define the angle ADB as theta, therefore the adjacent angle ADC must be equal to 180 degrees minus theta, according to rule number 1, that the sum of the angles on one side of a triangle, of a straight line, the sum of the angles on one side of a straight line is equal to 180 degrees. So if this angle is theta, the adjacent angle must be equal to 180 degrees minus theta. Then we implemented the law of cosines in the great triangle ADB, and also in the pink triangle ADC. What is the law of cosines? The law of cosines is true in any triangle. So this triangle ABC could be any triangle. The length of side AB is A units, side AC equals to B units in itself, and side BC equals to C units in itself, and angle BAC equals to theta. Then according to the law of cosines, C square equals to A square plus B square minus 2 times A times B times cosine theta. From this equation, it is very easy to arrive to this equation that cosine theta equals to A square plus B square minus C square over 2 times AB. So we implemented the law of cosines in the great triangle ABD. According to the law of cosines in this triangle ADB, cosine theta equals to d square plus m square minus c square over 2 times d times m. I repeat again, in the great triangle ADB, according to the law of cosines, cosine theta equals to d square plus m square minus c square over 2 times d times m. In the next step, we implemented the law of cosines in the pink triangle ADC. According to the law of cosines, in the pink triangle ADC, cosine 180 degrees minus theta equals to d square plus n square minus b square over 2 times d times n. I repeat again, in the pink triangle ADC, according to the law of cosines, cosine 180 degrees minus theta equals to d square plus n square minus b square over 2 times d times n. We have the trigonometric identity that cosine 180 degrees minus theta equals to minus cosine theta. Therefore, we substitute cosine 180 degrees minus theta by minus cosine theta in this equation number 2, and found out that according to equation number 2, minus cosine theta equals to d square plus n square minus b square over 2 times dn. We multiplied the equation number 1 by minus 1, cosine theta times minus 1 is minus cosine theta, and it is equal to minus inside the brackets we have d squared plus m squared minus c squared over 2 times dm. Then we created equation number, we have two expressions for cosine theta. Therefore, we created equation number 3 that says that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. Cosine theta according to equation number 1 equals to d squared plus m squared minus c squared over 2 times dm. And it must be equal to cosine theta according to equation number 2. Cosine theta according to equation number 2 equals to d squared plus n squared minus b squared over 2 times dn. Then we multiply this equation and equation number 3 by 2d. So in this side of the equation number 3 we have 2d over 2dm. Here 2d we get cancelled. We left only with m in the denominator. The numerator didn't change. It stays in the same expression. It's minus d squared plus m squared minus c squared. And it is equals to, we multiplied also this side of equation number 3 by 2d. 2d over 2dn is n. So in the denominator of this side of equation number 3 we left only with n. The numerator didn't change. It is the same expression. It's here, d squared plus n squared minus b squared. Then we cross multiplied this equation number 3 and we found out that according to equation number 3 minus n times d squared plus m squared minus c squared equals to m times d squared plus n squared minus b squared. Then we open the brackets on both sides of this equation number 3 and found out that minus n times c squared is minus n d squared, minus n times m squared is minus m squared, and finally minus n times minus c squared is plus n c squared, while minus times minus is plus. We open the brackets also of this side of equation number 3. We have here m times d squared is m d squared, m times m n squared is m n squared, and finally m times minus b squared is minus m b squared. Then we added to this equation number 3, n d squared. So we will focus on this side of equation number 3. We added n d squared. So we have n d squared minus n d squared is 0. We added also m n squared, n m squared. So here n m squared plus n m squared minus n m squared is 0. And we subtracted also n c squared. So we have here n c squared minus n c squared is 0. So in this side of equation number 3 we have to 0. In the other side of equation number 3 we have already had the expression of md squared plus mn squared minus mb squared, and we have to add to this side of equation number 3 also nd squared. We have also to add nm squared, and we have also to subtract from this side of equation number 3 and the nc squared. Okay, then we took this square, we took out the second factor from md squared and also from nd squared. So inside the brackets we left only with m plus n. Then we took out a common factor nm from nm squared and also from mn squared and also from nm squared. So inside the brackets we left only with m plus n, and we have also here minus mb squared and also minus nc squared. This is equal to 0. In the next step we added to this equation number 3 mb squared plus nc squared. So in this side of the equation we have mb squared plus nc squared, and in this side of the equation we have d squared plus n times mn times m plus n. Then we took m plus n as a common factor out of these two expressions. So inside the brackets we left only with d squared plus m plus n, that is equal to b squared n plus c squared n. We have already found out in the first method that m plus n equals to a, so we substitute m plus n by a in this equation number 3. So we have here n plus n, that is a, and inside the brackets we have d squared plus mn, that is equal to b squared n plus c squared n. Here a is m plus n. Inside the brackets we have d squared plus mn, that is equal to b squared m plus c squared n. And this is exactly the Stewart's equation. So we succeeded to prove Stewart's equation in two different methods. Okay, thank you very much.